Welcome to another episode of Mastering Cybersecurity, developed by baremetalcyber.com. Let's dive in. Containers changed how software is packaged because they bundle an application with everything it needs to run, which makes moving it between laptops, test servers, and clouds surprisingly smooth. The trade-off appears because many small units run together on one operating system, OS, kernel. So isolation depends on careful settings rather than heavy walls. For beginners, it helps to picture many sturdy lunchboxes stored in the same fridge, neatly separated but sharing the same cold air. That shared kernel means a mistake in one container, or in the host setup, can put neighbors at risk in ways different from old virtual machine habits. A simple mental model is that container security tries to reduce what each box can do, prove what is really inside it, and control how boxes talk to each other. With that frame, the core practices become easier to understand and apply consistently. A container is a running instance of a packaged application that looks like a tiny computer but borrows the host's OS kernel instead of bringing its own. A virtual machine, VM, imitates a full computer, including its own kernel, which creates stronger isolation but more overhead. Containers feel lighter because a container runtime starts processes with special isolation features, and a registry stores the images those processes use. An image is a read-only recipe with layers that describe files, libraries, and the default command. An orchestrator, such as Kubernetes, schedules many containers, restarts them when they crash, and exposes them on the network. Understanding these building blocks clarifies where controls should sit and how they reinforce each other. Container images are built from instructions in a file like a Docker file, which layers a base image, packages, and application files into a reusable artifact. Builders tag images with names like app 1.2.3 or app latest, but the tag is only a label which can be moved, while the immutable digest is a cryptographic fingerprint that proves the exact contents. Pulling by digest reduces surprises because you always get the same bytes the image author produced and tested. Storing images in a private or trusted registry lowers the chance of pulling something tampered or abandoned. Teams commonly keep a promotion path where images move from development to staging to production registries after checks pass. Thinking in terms of repeatable recipes and unchanging fingerprints helps keep environments predictable and debuggable. Containers achieve isolation through Linux namespaces and control groups, which change what a process can see and how many resources it can use. Namespaces carve separate views of things like process identifiers, network interfaces, and mounted file systems, so each container sees a private world. Control groups, often called C groups, limit CPU, memory, and input-output so noisy neighbors do not starve others or crash a host. Because all containers still share the same OS kernel, kernel bugs or overly broad privileges can break the illusion of separation. Rootless containers improve the situation by mapping the container's root user to an unprivileged user on the host through user namespaces. This design reduces blast radius if a process escapes, although it must be paired with sane defaults and careful host configuration. Supply chain security tries to prove who built an image, what source created it, and whether it was changed along the way. Signing images attaches a cryptographic signature that consumers can verify before pulls or deploys proceed, which prevents untrusted artifacts from sneaking in. Provenance attestation records which builder, source commit, and steps produce the image, enabling policy engines to require only known pipelines. Vulnerability scanning checks images and base layers for known issues so teams can rebuild with patched versions instead of carrying old bugs forward. Registries can enforce policies such as allowing only signed images, blocking critical vulnerabilities, or quarantining unknown publishers. Together, these controls build a chain of custody so production systems run only what factories intended to ship. Secrets management deserves special care because credentials are the keys to data and services, and containers can multiply where those keys end up. Store secrets outside images in a dedicated secret system and inject them at runtime through environment variables or mounted files that never land in the image layers. Encrypt secrets wherever they rest and restrict which service accounts or pods can request which secrets to reduce accidental exposure. Rotate secrets on a schedule and on incident because stale credentials tend to leak and linger in backups and logs. Ensure debugging practices do not print secrets to logs, which often get centralized and retained longer than expected. With these patterns, secrets stay close to the vault and far from places attackers and auditors both dislike. Networking for containers starts simple but quickly spans many paths, so guardrails help keep traffic focused and understandable. Default deny rules stop unexpected flows, then allow specific communications, such as a web pod speaking to an internal API and a database on a known port. Limit egress so workloads cannot call random external sites, which reduces data exfiltration paths and command and control callbacks. In Kubernetes, network policies describe which pods may talk, and a service mesh can add consistent encryption, identity, and per-request controls between services. Segment administrative endpoints from public paths and prefer cluster internal addresses for internal traffic which never needs to leave. When the map of allowed flows is short and explicit, troubleshooting and incident containment both become less chaotic. Runtime protection watches containers while they work, because even clean images can misbehave once exposed to the real world. Resource limits on CPU and memory prevent runaway tasks from choking a node and signal when usage suddenly spikes in suspicious ways. Drift detection alerts when a running container differs from its expected image or command line, which often reveals ad hoc debugging or compromise. System call monitoring can flag unusual behavior, such as a web process suddenly trying to load kernel modules or mount new file systems. File integrity monitoring on critical paths, combined with read-only routes, helps detect attempts to plant tools or rewrite binaries. These signals give responders an earlier start, which typically reduces the scale and cost of cleanup. Orchestrator hardening matters because the control plane decides who can run what and where, which makes it a prime target. In Kubernetes, Role-Based Access Control, RBAC, defines fine-grained permissions for users and service accounts, and the default permission should usually be no access. Namespaces scope resources so teams cannot accidentally step on each other, and they make it easier to apply guardrails like quotas and policies. Admission controls evaluate new workloads before they start, enforcing rules such as disallowing privileged pods or requiring signed images. Pod security standards, PSS, offer baseline, restricted, and privileged policy sets that describe acceptable security settings for pods. Hardening also includes securing nodes, runtimes, and kubelets because a weak host undermines every careful control above it. Shifting security left brings checks into the build and delivery pipeline so weak images never reach production, which saves time and reduces noise. Continuous integration and continuous delivery (CI/CD) systems can lint Docker files for risky patterns like using latest tags, adding shells, or running as root. Image scanners run during builds and fail the pipeline when critical vulnerabilities appear, prompting developers to update base images or dependencies. Policy as code in the pipeline and at cluster admission keeps rules consistent across environments and prevents manual exceptions from sneaking in. Reproducible builds help teams rebuild the exact same image from the same source, which reduces drift and makes incident reconstruction easier. The earlier a problem is found, the cheaper and calmer the fix usually becomes. Monitoring, logging, and patching keep container environments healthy after deployment, because change and new vulnerabilities are constant facts. Centralize container logs with labels that include image names and digests so responders can tie events to specific builds. Track which versions of images and base layers are running across clusters, then rebuild and redeploy to patch rather than modifying running containers by hand. Host telemetry and container metrics together reveal whether issues come from the application, the node, or the orchestrator. Prepare an incident response runbook that maps container identities to owners, registries, and source repositories, which reduces confusion during stressful investigations. With disciplined observation and rebuild-based patching, environments stay understandable even as they evolve. A beginner-friendly checklist helps connect the moving parts into a stable day-to-day practice that does not require heroics. Reduce privileges in containers by avoiding root, dropping Linux capabilities, and using seccomp and read-only file systems whenever possible. Prove what runs by using trusted registries, immutable digests, signatures, provenance, and SBOM tracking. Then gate deployments using admission policies. Control connections with default deny networking, limited egress, and service identity so services only talk when they should. Keep builders and operators aligned by shifting checks into CI/CD and monitoring the runtime for drift and unusual behavior. Following these habits consistently yields fewer surprises because each control backs up another control without adding unnecessary complexity. It is worth strengthening the human and process side because containers make it easy to move fast and forget to coordinate. Establish image ownership so every running artifact has a responsible maintainer who receives vulnerability alerts and change requests. Set service-level targets for patch windows and rollouts, then measure how long vulnerable images remain in production after a fix is available. Teach developers the small patterns that pay big dividends, such as multi-stage builds and non-root users, so security becomes the default, not an exception. Run steady tabletop exercises where teams walk through a kernel vulnerability or a leaked token scenario and practice the rebuilds and rollouts. When people share the same simple playbook, the platform stays secure even as teams and services grow. Finally, remember that host and kernel hygiene underpin every other choice because the shared kernel is the ultimate common point. Keep hosts minimal, patched, and dedicated to running containers rather than acting as general-purpose servers. Use timely kernel updates and consider mechanisms like live patching where appropriate to reduce risky windows without long outages. Limit who can access nodes and runtimes and protect their credentials as carefully as production database passwords. Treat the container runtime and orchestrator components as Tier 1 services with their own monitoring and update plans that are tested, documented, and reviewed. When the bedrock stays strong, the lighter container isolation model maintains its promises under normal and stressful conditions. In recap, container security focuses on reducing privilege inside each container, proving the exact software you run, and controlling how workloads connect. The shared kernel makes discipline around isolation, image trust, and host hardening more important than in heavier VM designs. A small, memorable routine helps beginners succeed. Run with less, verify before you trust, and allow only intended conversations. With those 3 habits in mind, the rest of the details in mind arrange themselves into a dependable, day-to-day practice. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.